Hello everyone, welcome to second lecture of concept to project. Through this video series, we will try to design the floating point multiplier which will be our project. And what our concept is here? Our concept is the Vedic Mathematics Sutras, that Urdhwtirgbhyaam. So in this second video of concept to project, we will see the binary multiplication based on Urdhwtirgbhyaam Sutra. So as we start with concept and we will end with design. So our concept is Vedic mathematics, that one of the sutras, Urdhwtirgbhyaam, and we will end with design the floating point multiplier. And these are the various steps that we have to go through this process. From this Vedic mathematics concepts, we will go with that binary multiplication, we will relate it, then we will implement this binary multiplier using logic gates and adders. After that we will make fixed point multiplier for integer value and then floating point multiplier. So in this video we are looking for binary multiplication based on Vedic Mathematics Sutras, Urdhwtirgbhyaam. So before going for a binary multiplication, we should know what the binary number is. So binary number system having the basis 2, which has the symbols or the values are 0 and 1. That means we can say having a two states, on and off. When we say it's on, we will take a logic 1, and when we say it's off, that means we can take the logic 0. Each digit of binary number system is known as bit. Other than binary number, as already we know that there is a decimal number having the basis 10. What the symbols or what the values we are using, that is from 0 to 9. Then octal having the basis 8, which has the numbers from 0 to 7. Total numbers are 8, or the total symbols are 8. Hexadecimal having that 16 symbols, the base is 16, and having the symbols are 16, 0 to 9, that are 10, and A, B, C, D, E and F are having 7 symbols. So that is 6. So 10 plus 6, 16. If we relate the Urdhwtirgbhyaam Sutra for binary multiplication, we should also know the relation between your binary and decimal number. So if I write the decimal number as 3, so what their equivalent binary is, that is 0, 1, 1. So how we can do this? So for that, very simple, the binary numbers comes in a group, if we say that, or the bit positions if they are having. So if you are having that 8 bits, that can be called as of your 1 byte, and their positions are going from here, that right to left. This is from right to left. So right bit position is 0th position, we can say, then first position, second position, third position, fourth position, fifth, sixth and 7. These are the binary numbers, or we can say that bit position. What their equivalent decimal weight with respect to their position, as if there is a decimal number, we can write their weight is from right to left is 10 to the power 0, 10 to the power 1, 2, 3 and so on. In the same way, the binary also having the binary is having the basis 2, so we can write their radix as 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4 and so on. So their equivalent decimal weight becomes 2 to the power 0 means 1, 2 to the power 1 means 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, then 2 to the power 5 32, 2 to the power 6 64, 2 to the power 7 is 128. So how we can convert that the binary number into decimal? So let's take example is, if you are having the binary number is 0 0 0 0 0 1 1 0. So when you are going to convert, you have to take the binary number, multiply with equivalent decimal weight at their respective position, plus second bit multiply with their respective position weight plus next bit and their respective equivalent decimal weight plus, and so on. So in this way we can convert that binary number into decimal number. So we can check here the equivalent decimal number for that 110. So what here 0 into 2 to the power 0 plus 1 into 2 to the power 1, or we can say that 1 into 2 also, plus 1 into 2 to the power 2 plus 0 into 2 to the power 3, 0 into 2 to the power 4, all are having that multiply with that 0. So indirectly we can say that the overall summation becomes 0. So only here the bits whose number is 1, so that we will consider. So 1 into 2 to the power 2, that is 4, then 1 into 2 to the power 1, so plus 2, and this is 0 into 2 to the power 0, that is 0. So 4 plus 2 plus 4 plus 2 plus 0, that is 6. So 110 is the binary equivalent of 6. So in the same way, if you are having that the binary of 101, so 101, that means the first bit is 1, that is 0th position bit is 1, so 1 into 2 to the power 0, then plus 0 into 2 to the power 1, so there is no meaning, that is multiply with that 0, plus 1 into 2 to the power 2. So 2 to the power 2 means 4, so 4 plus 2 to the power 1, 2 to the power 0 is 1, so 4 plus 1 is 5. So 101 is the equivalent of 5. So we are having some decimal numbers and their equivalent binary numbers. So decimal numbers start from 0, their equivalent binary is 4 times 0, 4 times 0, or that 4 bit we can say a nibble, and 8 bit we can say as 1 byte. So when we are having that 4 bit, so maximum how many of decimal numbers can have that 4 bit binary number? So how many of decimal numbers can cover with 4 bit binary numbers? So that is 2 to the power 4, so we are having that 16 decimal numbers or 16 symbols we can have in decimal. So that will start from 0, 1, 2, 3, 4, 5, 6 up to 15. So 0 to 15 becomes total 16. So 0, its binary is 0, 0, 0, 0, 1, 0, 0, 1, 2, 0, 0, 1, 0, 3, 4, 5, 6, 7, then 8, 9, 10, 11, 12, 13, 14 and 15. We start from 4 times 0, we end here that 4 times 1. So 4 bit binary number can represent from 0 to 15 decimal. Now you can check here, as decimal is having the symbols are 0 to 9 only. This is 0, start from 0 up to 9. Now from 9 to onwards, this 0 and so on, these are repeating, and these are repeating first time, so that's why we are putting here that 1. So 10 becomes 10, 11 becomes 11, 12, 12, 13, 14 and so on. In the same way, if you are looking for binary number 0 and 1, binary is having only that 2 digit 0 and 1, as 0 and 1 is over, so first time that will repeat, so we are putting here that 1 1. Okay, now 0 and 1 it is second time repeat, so 1 0 we are putting in front of them. Okay, then third time it is repeat, so we are putting there 3 in front of 0 and 1 and so on, and their equivalent decimal are here, that 0 to 7 and 8 to 15. Once we got the idea about the decimal numbers and binary, we can easily go for their multiplication. So binary multiplication of two numbers, and each number is 2 bit. So using the sutras Urdhwtirgbhyaam, what the general way of multiplication is, if you take the number is 1 1, that is the equivalent of 3, binary decimal equivalent is 3, then 1 0, 1 0 is the binary of 2. So first we multiply that 0 by this 1 1 bit, so 0 into 1 0, then 0 into 1, that is 0. Then when we do that general way of multiplication of that array type of multiplication, we just shift and add. So we shift here by 1 bit and we insert there 0 first. So 1 is multiplied with this 1 1, So 1 into 1 1, 1 into 1 1. Once we get this 0 0 and 1 1 0, after that we can add them. So 0 plus 0 0, 0 plus 1 1, there is no carry, and then 0 plus 1 as it is. As there is no carry for that 0 plus 1, so here we can write that 0. 2 by 2, 2 by 2 multiplication, so we are getting the result is 4 bit. This is of your general way of multiplication. For 2 bit multiplication, it's very simple. It is also known as the array type of multiplication. But when the number of bits are more or it is increases, that is 4 bit, 5 bit, 8 bit, or even we are having the processor is 32 bit or 64 bit, then that times it will time consuming. It will have that more delay, and that's why we can go with that multiplication by Urdhwtirgbhyaam. That will be more efficient than the array multiplier. Now, how we can do the multiplication in by Urdhwtirgbhyaam Sutra? So let's take the same number 1 1 and 1 0, that is the decimal. 1 1 is the decimal of 3 and 1 0, their equivalent decimal is 2. So how we can do that, the Urdhwtirgbhyaam, as already we have seen in the previous video. So first we start with that right hand side column entries or right hand side that digit. So 1 into 0, so step 1 is 1 0. 1 into 0, that is of your step 1. So 1 into 0, that equals to 0. This 0 we will take it in that the final result, the first bit we got here, that's 0. Then cross multiplication and their addition. So 1 into 0 plus 1 into 1. So step 2, 1 into 0 plus 1 into 1. So that becomes 1 into 0 is 0 plus 1, it becomes 1. As there is no carry, so we can keep the carry as 0. So sum can be written in the result, and the carry out, as actually here that carry is 0. So that will be carry out in step 3 addition. So what is your step 3? Step 3 is the last bit multiplication. So 1 into 1. So step 3, 1 into 1 plus previous bit, previous step bit, here we add. So 1 into 1, 1 plus 0, that is 1. So it can be represented as the carry is 0 and sum is 1. So we can keep this is in the result. So we got here 1 1 into 1 0, that is 3 into 2. So it becomes 6. So whether it is equivalent, whether it is the binary of 6 or not. So we can check here 0 0 multiplied by 2 to the power 0, that is 0, plus 1 into 2 to the power 1, that is 1 into 2, and here 1 into 2 to the power 2, that is 4. So 4 plus 2 is 6. So it's okay. If you are having a 3-bit binary number, so how we can do that multiplication? Let's take the number is 101 and 111. 101 is the binary of 5 and 111 is the binary of 7. So 5 into 7, as everyone know that the multiplication of 5 into 7 is 35. So whether we will get the result is 35's binary or not. So let's check here. So again, first we multiply the first digit. So 1 into 1, that is step 1. So 1 into 1, 1. Then second step is keep this 1 is in the result, that is the first bit. Then second step, cross multiplication of that first 2 bit and their addition. So 0 into 1 plus 1 into 1. So 0 into 1 plus 1 into 1, that is 0 plus 1 is 0 1. 0 is carry and 1 is sum. So keep your sum in the result, and that 0 will be carried out in that step 3 addition. What is your step 3? Multiplication of your all diagonal elements. So 1 into 1 plus 1 into 1 plus 0 into 1. So 1 into 1 plus 0 into 1 plus 1 into 1 plus previous bit addition from step 2 plus 0. So 1 into 1 is 1 plus 0 into 1 is 0 plus 1 into 1 is 1 plus 0. So 0 plus 1, 1, 1 plus 1, 1 0 plus 0. So your result you are getting that 1 0. So 1 is carry and 0 is sum. So keep your sum is it in the result, and 1 will be carried out to next step. So what your step 4 is? Step 4 is the last two bit cross and add, cross multiplication their addition. So step 4, 1 into 1 plus 0 into 1 plus previous bit, that is previous bit carry from step 3. So 1 into 1 is 1 plus 0 into 1 is 0 plus 1. So 1 plus 0 1, 1 plus 1 1 0. So carry is 1 and sum is 0. So keep the 0 in the result and the carry out will be add in step 5 addition. So what is step 5? Step 5 is the last bit multiplication, 1 into 1. So step 5 is 1 into 1 plus previous bit from step 4. So 1 into 1 is 1 plus 1. So 1 plus 1 is 1, carry 1 and sum is 0. So keep the final result in, keep the step 5 result in the here. The bits are here. So we got here the result is 1 0 0 0 1 1. This is our final multiplication result. Whether this binary is of 35 or not, let's check. So first bit is 1, so 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 to the power 2 to the power 3 to the power 4 and to the power 5. So 1 into the power 5. To the power 5 is 32 plus to the power 1 is 2 and to the power 0 is 1. So 32 plus 2 34 plus 1 that is 35. It means 5 into 7 we get here that 35. So this Urdhwtirgbhyaam Sutra is working better for 3 by 3 bit multiplication even also. If you are looking for 4 by 4 bit multiplication, so how we can do it? As already we done with the 2 by 2 bit multiplication. So whenever we are having that large bit numbers or large digit numbers, we can divide it in its half. So if you are having that 4 by 4 bit number, so we can divide that number in a pair of bits or 2 bit and 2 bit. So we can have 1010 we can divide in that 2 bit pair. So 10 and 10. That means whenever we are having that n number of bits, so we may divide that n number of bit by n by 2 number of bits. So in place of directly n bit multiplier, we can also achieve it by n by 2 bits multiplier. How we can do it? Let's check. So 1010 into 1101. So we divide that 1010 into 10 of first bit pair, another 10 is another bit pair. In the same way 1101. So we divide in that 11 and 01. So again we follow the same sutras, Urdhwtirgbhyaam. So first we multiply the right side bit pair, then cross and add, and then left side. So step 1, whatever step 1 is 10 into 01. As 10 into 01 is 2 bit by 2 bit multiplier, so whenever we are going for that 4 by 4 bit multiplier, we have to use there that 2 bit multipliers, 2 bits multiplier. So 10 into 01 we are getting here that 0011. Out of that the 10 we have taken in the result. Whenever we are having that 2 bit by 2 bit multiplier we use there, then that means we have to take that 2 bits in the result, first 2 bits, and last 2 bits will be add in the step 2 addition. So what your step 2 is? Our step 2 is cross and add. So 10 into 01, 10 into 01, and then 10 into 11. So 10 that is 2 into 1 that is 2 plus 2 into 3 that is 6 and plus 00. So we get here the result is 2 plus 6 is 8. Again out of that 1000 we take here the first 2 bits in the result and the last 2 bits that will be add in step 3. So what is step 3? Step 3 is the last pair multiplication, 10 into 11. So 10 into 11 plus this 10 from the step 2. So 10 into 11 plus 10. So we get here that 2 into 3 6, 6 plus 2 8. So it's equivalent of 8, and keep this step 3 result in the final itself as it is. So we get here 1 0 0 0 0 0 1 0. So what that 1 0 0 and so on, whatever that result is, their equivalent decimal number is. So what here? 0 into 2 to the power 0, that is 0. First position, that is 1. Here the first position, this is 0th position, this is first position. So 1 into 2 to the power 1, 2 to the power 2, to the power 3, to the power 4, to the power 5, to the power 6, and to the power 7. So 1 into 2 to the power 7 also. So 2 to the power 7 is nothing but 128 plus 2 to the power 1 is 2. So 128 plus 2, that is 130. So its equivalent decimal number is 130. So it is the binary of 130. What here 1010? 1010 is the equivalent of 10. 1101 is the equivalent of 13. So 10 into 13, we get here that equivalent of 130. So it's correct. So look at here, when we are doing the multiplication of 4 bit by 4 bit. So what here? We need 2 bit by 2 bit multiplications. This is the first multiplier of 2 bit by 2 bit. We need here that second multiplier. We need that third 2 bit by 2 bit multiplier, and we need that fourth multiplier. So when we go for that 4 by 4 bit multiplications, we need that 4 times 2 bits multiplications. And this is the things that we will implement using this logic gates and adder in next coming lecture. So you enjoy this video and do subscribe for new updated video. So we will be continue with next video. Thank you for watching.